Come closer, friends. Let's take a slow breath and look up. The sky may be cloudy where you are, or bright and blue, but above it all hangs our star, the Sunday. It feels safe, like a steady friend at the window, yet inside that warm light live quiet storms that can reach across space and touch our little world. In this episode, we'll walk from the surface of the sun down to its hidden heart, then ride the winds it sends out and see how they nudge our satellites, our GPS, and our plans to explore. If gentle, curious journeys like this speak to you, a quick like and subscribe keeps us traveling together. Ready? Let's begin. Imagine a quiet hill at daybreak. The first light touches your face, soft and warm, while the sky slowly fills with gentle color. Those colors feel like the whole story, but they are only the ending. The light that reaches your eye has crossed the air above you, the space between Earth and Sun, and the many layers of the Sun itself. It began deep inside a nuclear furnace that has burned for billions of years. The Sun was born in a cloud where earlier stars lived and died. Their remains gathered, squeezed by gravity, and lit again. Today, that sphere of hot, charged matter powers our days and sets the rhythm of our lives. To understand it, we can follow the light backward, from your retina to the atmosphere, across open space and into the star. We begin at the edge and work inward, like peeling a piece of fruit. The outermost visible part of the sun's atmosphere is called the corona. Corona means crown, and that is what it looks like during a rare total solar eclipse, a pale, ghostly halo around a dark circle. For a few minutes, when the moon lines up just right, the bright surface of the sun is blocked, and the corona steps forward. To the unaided eye, it seems smooth and delicate, but it is not simple, and it is not calm. Spacecraft see far more than our eyes can. NASA's Solar Dynamics Observatory, SDO for short, was launched in 2010 to watch the sun in many kinds of light, including wavelengths our eyes cannot see. When we look at extreme ultraviolet light, such as the 19.3 nanometer band, patterns appear in the corona. That wavelength traces gas that is roughly 1,000,000 degrees in temperature. Bright arcs and fans show magnetic fields reaching out, looping back, and shaping the hot, thin atmosphere that surrounds the star. Seeing the corona in this light turns a smooth halo into a living map. The sun is not a quiet ball with a calm shell. It is a magnetic engine. The gas in the sun is a plasma matter so hot that atoms split into free electrons and ions. Plasma responds to magnetic fields the way iron filings respond to a magnet. It lines up, flows along invisible paths, and sometimes gets tangled. Where the tangle grows, energy builds. In bands that highlight even hotter gas, tens of millions of degrees, we notice sudden bright flashes. These are solar flares, bursts of high-energy radiation created when magnetic field lines cross, snap, and reconnect. This magnetic reconnection is like a stretched rubber band that finally lets go. The energy stored in the field turns into light and heat in an instant. Flares can come in clusters. In August 2022, for example, space weather monitors recorded a busy stretch with many flares rising and fading across active regions on the Sunday. A flare is mostly radiation, X-rays, and ultraviolet light that race outward at the speed of light. Sometimes, though, the magnetic change is strong enough to push matter as well. That event is called a coronal mass ejection, or CME. A CME is a cloud of plasma electrons and ions lifted from the sun's outer atmosphere and hurled into space. These clouds can weigh billions of tons and move at hundreds to thousands of kilometers per second. A flare can happen without a CME, and a CME can happen without a strong flare, but they often travel together from the same active zone, like a flash and a gust from the same storm cell. The sun vents energy in quieter ways too. In some places, the corona has holes. A coronal hole is a darker patch in extreme ultraviolet images. It is not a gap in the star, but a region where the magnetic field lines open outward instead of looping back to the surface. Open field lines are like straight lanes on a highway. Charged particles escape more easily along them. From these regions, the solar wind, the constant flow of particles from the sun, speeds up and pours into space. When a fast stream from a coronal hole catches up with slower wind ahead of it, the boundary can rattle Earth's magnetic field. The result near our poles is aurora, curtains and arcs of light, dancing where the atmosphere and magnetism meet. Using light our eyes cannot see is like adding new senses. Different wavelengths bring out different structures and temperatures. Extreme ultraviolet reveals hot arches, fans, and sheets. Within this outer atmosphere, we also find long, looping forms called prominences when seen above the limb, and filaments when they lie across the sun's face. These are great arcs of plasma held up by magnetic fields, like glowing threads draped across a magnet's field lines. Some loops could hide our planet inside them many times over. They can form in a day, and, if stable, last for weeks or months, slowly changing as the underlying fields evolve. A time-lapse view helps us feel their motion. In sped-up footage, a prominence rises from the region we call the photosphere, the bright surface, and climbs into the corona. Even while time is compressed, the motion is swift when you remember the scale. Magnetic fields are doing the lifting and guiding. The same fields can create another gentle-sounding but dramatic effect called coronal rain. Plasma in loops can cool, condense, and fall back along the same paths, shining as it descends. It is rain, only by analogy. The material is still extremely hot, by Earth standards thousands to tens of thousands of degrees, and the droplets are strands of plasma, not water. The image of rain helps us imagine the flow without confusing it with weather as we know it. Sometimes the loops cannot hold. A structure will build for hours or days, twist tighter, and then break. When it snaps, a CME can launch. In time-lapse, you see a ridge or arch near the edge of the sun swell, tear, and surge away. If that cloud travels toward Earth, most of it is turned or slowed by our planet's magnetic field. Yet a strong hit can still disturb satellites, radio links, and power systems. Engineers watch for these events and plan for them, and missions like SDO help by showing where and when the sun is active. Images taken near the 30-nanometer band, another extreme ultraviolet range, are especially useful for tracking these outer structures because they light up the patterns that matter most for space weather. The sun is too complex to understand from a single view. Two images taken at the same time can tell very different stories if they use different wavelengths of light. One channel that traces gas around 600,000 degrees tends to show quieter coronal loops, long arcs that rise and fall smoothly. Another that highlights gas around 2 million degrees lights up the hot cores of active regions where fields are tight and energy is stored. Place these images side by side and you see contrast. Serene loops in one, bright knots and sparks in the other. The lesson is simple and deep. The sun is layered in temperature and structure. What looks like a single feature in one band is revealed as a chain of linked events when seen in another. That is why we stack views and watch over time. Working inward, we meet a thin but important layer called the transition region. As the name suggests, It links the outer corona to the chromosphere below. It is shallow, on the order of 100 kilometers, but it holds a sharp rise in temperature. In a short vertical distance, the gas goes from thousands of degrees to hundreds of thousands. In images around 160 nanometers, we see a mottled pattern that marks this boundary. The physics here is tricky. Radiation, conduction, and waves all move energy, and magnetic fields guide the flow. What matters for us is that this region is where the sun's atmosphere flips character. Above it, the corona is hot and very thin. Below it, the chromosphere is cooler but still far hotter than anything on Earth and thicker. The chromosphere is the next stop inward. This is the last layer of atmosphere above the bright surface. It is thicker than the transition region, roughly a couple of thousand kilometers, and shows a dynamic texture in ultraviolet light, such as 170 nanometer images. In close views, we notice thin spikes sprouting everywhere. These are spicules, jets of plasma that shoot upward from the lower atmosphere. They rise like blades of grass in a strong wind, although each blade is longer than whole countries. Spicules can reach heights of many thousands of kilometers and speeds up to about 100 kilometers per second. They form and fade within minutes, constantly renewing the forest of fine structures that cover the Sunday. For years, scientists debated how spicules launch against the pull of gravity and the grip of magnetic fields. Charged particles in a plasma usually trace magnetic field lines. They do not easily cross them. A key insight came from detailed models published in 2017. Those models added neutral atoms, particles with no net electric charge, to the mix. Neutral particles are not tied to magnetic field lines. They can drift and push. In the models, the neutrals mixed with ions and electrons, briefly dragging the charged particles upward and giving them the lift they needed. The result was a jet that looked and behaved like a spicule. The simple idea is that neutrals act like a crowd moving through a fence. They do not get caught by the bars and can pull others along. Below the chromosphere lies the photosphere, the layer our eyes see as the surface. It is not a solid surface, though it may look sharp from a great distance. The photosphere is only a few hundred kilometers thick. It is where the gas becomes tense enough and cool enough to shine strongly in visible light and to let light escape into space. This is the deepest layer we can observe directly with light. Everything below is hidden from view and must be probed with indirect methods like vibrations and neutrinos. Here, it helps to repeat a key point. The sun is made of plasma. At the temperatures inside the star, matter is not solid, not liquid, and not ordinary gas. Electrons are free from their atoms, and the mix of ions and electrons responds to electric and magnetic forces as much as to pressure and gravity. If we could hover just above the photosphere and take a close look, we would see a grainy pattern, like boiling oatmeal. The bright cells are places where hot material rises. The darker edges show where cooler material sinks. This pattern is called granulation and comes from convection, the up and down motion that moves heat. On top of this pattern, we see darker spots. These are sunspots. Sunspots look dark only by contrast. They are cooler than the areas around them because strong magnetic fields there block some of the convective heat from below. A sunspot is a magnetic structure first, a thermal feature second. The field lines are so concentrated that they reduce the updraft of hot plasma. The spot, starved of fresh heat, settles to a lower temperature and glows less brightly. Some spots are small, like pores. Others grow into systems larger than Earth. Sunspots are not random. They appear in bands on either side of the sun's equator. shift in latitude over time, and rise and fall in number according to the sun's activity cycle. When we compare a visible light image of the photosphere with an extreme ultraviolet image taken at the same time, a link becomes clear. Many of the bright, explosive events in the outer atmosphere line up with active sunspot groups below, where the field is strong and twisted near the surface. Flares and sometimes CMEs follow higher up. One structure leads to the other. This chain from photosphere to chromosphere to transition region to corona shows why multi-wavelength imaging matters. A feature at one level is rarely isolated. A spot on the surface implies stressed fields above it. Those fields shape loops and arches. Where loops interact, they can reconnect, releasing energy as flares. If the balance breaks, a filament can lift and become a CME. Open fields in coronal holes feed the high-speed solar wind. When that wind, or a CME, reaches Earth, our magnetic field is stirred, and auroras light the night. The physics that begins in a patch the size of a continent can end with light in our polar skies and a small change in the drag on a satellite thousands of kilometers above us. Returning to the light that began this path, we can say this much with care. The colors of sunrise are the last step of a long trip. The photons scatter in our air, painting red and orange because of the way shorter wavelengths bounce more. Before that, the light crossed the space between Sun and Earth about 1 astronomical unit, an average distance of roughly 150 million kilometers. Before that, it was released in the photosphere after a far longer journey inside the star. The energy that became that light started as nuclear energy from fusion in the core, made its way through the radiative zone by countless steps, then rose through the convective zone in great cells of moving plasma. We cannot see those inner regions directly here, but the surface and the layers above it carry the signs of the engine below. The magnetic fields that shape the corona are anchored in the churning motions beneath the photosphere. We have only traced the outer layers and the surface so far, using tools like SDO's views in extreme ultraviolet and near ultraviolet light. These tools let us separate temperatures, highlight patterns, and follow motion with time-lapse sequences. They also remind us to be cautious. A single image can be beautiful and misleading. 2 or 3 images together, taken at different wavelengths, reveal structure and cause. Quiet loops become active arcs when seen in hotter bands. Dark holes become highways for wind. Bright knots mark intense magnetic fields where flares are more likely. By stacking views and watching over days and weeks, patterns emerge that a snapshot cannot show. When we teach these ideas, we often rely on pictures. The eclipse corona becomes a crown. Prominences become ropes or bridges. Coronal rain becomes glowing drizzles sliding along rails. These images are helpful because they connect the strange to the familiar. Yet it is important to keep the differences in mind. There is no air in the corona. There are no clouds in the sense we know them. There is only plasma guided by magnetism, heated by waves and reconnection, cooled by radiation, and always in motion on a giant scale. The sun's outer atmosphere is a laboratory where the rules of electricity and magnetism play out in plain view. From this vantage, the story returns to the surface, where magnetic fields knot, sunspots rise. Above the same regions, bright loops arch and flares flash, while open-field coronal holes feed the wind. These are parts of one linked system that waxes and wanes with a clear rhythm over years. To read that rhythm from afar, we tie layers together, what we see in the corona with what the surface is doing where those fields anchor. Up close, a sunspot is more than a dark patch. In high-resolution blue light near 400 nanometers, the area around it is tiled with rough-edged, ever-shifting cells about 1,000 kilometers across. These are solar granules, the tops of boiling convection cells. Hot plasma rises in the bright center of a granule, spreads when it reaches the surface, cools, then sinks along the darker lanes that outline each cell. Where the magnetic field is strongest, that upflow is partly blocked, so the spot looks darker against the churning background. The cycle repeats without pause, turning the photosphere into living texture that feeds and helps explain the activity above. This motion is not gentle. A typical granule lives for only about 20 minutes before it fades and a new one takes its place. Yet the flows inside can move at several kilometers per second, faster than sound in that thin gas. Those fast flows drive shock waves that ripple across the surface in full disk images that look grainy. The grain is not digital noise. It is this field of granules, each one rising and falling like a slow, constant boil. Sunspots sit inside this restless sea. Their strong magnetic fields block some of the rising heat, so the spot looks darker by contrast, while the bright granules continue to churn around it. Direct imaging stops at the photosphere. Light, visible and invisible, cannot show us layers deeper than this, at least not with a simple picture. Below the surface, we switch to indirect tools that read the sun's vibrations or catch rare particles from the core. Even so, the lesson from the outer layers is clear. Using different kinds of light changes what we can see, and putting those views together turns a flat picture into a story of cause and effect. With that habit in mind, it helps to step back and ask where this engine came from and how it first turned on. Long before Earth formed, there was a cold, dark cloud in our part of the Milky Way. Astronomers call this a giant molecular cloud, a mix of gas and dust spread across many light years. It held mostly hydrogen and helium, the simple elements that make stars, but it also held heavier elements such as carbon and oxygen. Those heavier elements were leftovers from earlier stars that had lived, died, and exploded. In time, a shock perhaps from a nearby supernova ran through the cloud and squeezed parts of it. Where the squeeze was strongest, gravity took over and began to pull matter inward. Some researchers even gave that possible trigger a name, Quetzalcoatl, after a goddess linked with death and birth, to capture the idea that the end of one star can seed the beginning of another. As the cloud shrank, it did not collapse into a single object. It broke into many dense knots. The reason is simple physics. Inside a cloud, gravity tries to pull material together, and pressure tries to push it back out. There is a critical size, often called the Jeans length, where gravity wins. Regions larger than that size begin to fall in on themselves. Because density and temperature are not the same everywhere, different patches cross that threshold at different times. Each patch becomes its own collapsing core. One of those cores would become our Sunday. In the earlier stage, the center was a protostellar core, a seed of a future star wrapped in falling gas and dust. Gravity pressed the seed tighter. As it shrank, it heated up, and the warm core began to glow from the energy of its own contraction. This was not yet a true star. There was no fusion in the center, but light and heat already leaked out, powered by gravity's work. Nothing in space is perfectly still. The original cloud had a tiny amount of spin. As the material fell inward, conservation of angular momentum, nature's rule that spin speeds up when spread out mass pulls in, made that slow turn faster. Picture a figure skater drawing in their arms to spin quicker. Around the equator, Some of the infalling gas was moving fast enough to miss the center and go into orbit, above and below, where the motion did not match the new spin. Material kept falling straight in. The result was a flat, turning disk around the newborn star. We call it a protoplanetary disk. Inside that disk, dust clumped, collided, and grew. Some pieces were ground to bits and fell inward to feed the star. Other pieces survived to become the planets, moons, asteroids, and comets we know today. For millions of years, the core of the infant sun kept contracting and heating. Deep inside, the pressure and temperature climbed until the center reached the threshold needed for fusion. At about 10 million degrees or so in the core, hydrogen nuclei protons began to join to form helium. When that reaction started in earnest, a star was truly born. From then on, energy from fusion pushed outward against gravity. The push and the pull balanced. This state of balance is called hydrostatic equilibrium, inward gravity matched by outward pressure. With that, the sun settled onto the main sequence, the long, steady phase of a star's life, when fusion in the core supports the star's weight. The balance could not exist without a steady energy source, so it helps to look at what fusion is up against. Inside the core today, the temperature is on the order of 15 million degrees, and the pressure is extreme. The atoms there are stripped of electrons, leaving a plasma of protons and electrons. Protons carry positive electric charge, and like charges, repel. This electric push is the Coulomb force. It is why the same ends of two bar magnets refuse to touch, an everyday example of repulsion. For two protons to fuse, they must get close enough for a different force to act. The strong nuclear force binds protons and neutrons together in atomic nuclei, but it acts only over a very small distance, about a femtometer, which is a million billionth of a meter. The problem is getting two protons close enough for the strong force to snap on while they are pushing each other away. If we relied only on classical physics, the numbers would look impossible. The core would need to be far hotter to let most protons climb over the electric barrier. Early calculations in the 1920 seconds seemed to say fusion could not work at the sun's observed temperature. The mystery faded when quantum mechanics changed how we think about particles. In quantum thinking, a particle can also behave like a wave. Instead of a single path, there is a spread of possible positions with different probabilities. This opens a door called quantum tunneling. A proton does not have to go over the top of the energy barrier. There is a small chance it will tunnel through and appear on the other side. Most attempts fail, but in the crowded, hot core, there are so many tries that enough succeed to keep the star running. Once two protons get close enough, the strong nuclear force can bind them, but not in a simple way. The sun mainly uses a sequence called the proton-proton chain. It begins when two protons fuse. One of them changes into a neutron in the process, and the pair becomes a deuterium nucleus, one proton plus one neutron. A positron, the antiparticle of the electron, and a neutrino, a tiny, neutral particle that rarely interacts with matter, carry away some energy. The new deuterium nucleus quickly grabs another proton to make helium-3, releasing a high-energy photon called a gamma ray. In the last step of the main branch, two helium-3 nuclei bump into each other and fuse to make helium-4, while two spare protons are freed to try again. Piece by piece, mass turns into energy according to Einstein's E equals mc squared, and that energy works outward as light and heat. There is another fusion path as well, more important in stars hotter and heavier than the Sunday. It is called the CNO cycle because carbon, nitrogen, and oxygen act as helpers or catalysts. In this cycle, a carbon nucleus picks up protons in steps, turning into nitrogen and oxygen and back to carbon, while helping to fuse hydrogen into helium. In our Sun, the CNO cycle makes only a small share of the total energy. In larger, hotter stars, it can dominate. Either way, the physics is the same. Gravity squeezes, fusion pushes back, and the star finds a steady size and brightness for a long span of time. Thinking about the path from cloud to core helps explain features we saw at the surface. The same rotation that made the disk also affects the star's magnetic field. Inside the Sun, heat moves outward in two main ways. In the deep radiative zone, energy steps outward as photons scatter again and again, closer to the surface. In the convective zone, hot plasma rises and cooler plasma sinks, like water in a pot. Those large, slow cells help wind and twist magnetic fields. Where the fields bunch up at the surface, sunspots appear. Above those regions, loops form in the outer atmosphere, where loops cross and reconnect. Flares flash and sometimes a CME lifts off. The chain reaches from the core, where fusion powers the whole system, to the corona, where open field lines become paths for the solar wind. The numbers that define these processes can be intimidating, so it is useful to keep only a few anchors in mind. Granules are roughly 1,000 kilometers wide and live for minutes. Shock waves from fast flows ripple across the photosphere. The thin transition layer above the chromosphere sees a sharp jump in temperature over a very short height. Prominences can arch tens of thousands of kilometers into space. A CME can carry billions of tons of plasma outward. The core is hot enough and dense enough for quantum tunneling to make fusion possible, even though protons repel. From these simple notes, the rest is pattern. The Sun's behavior is not random. It follows rules that we can describe, test, and refine. All of this returns us to the light that meets your eye. A photon that warms your cheek at sunrise began as energy released deep in the core, then wandered through the radiative zone, rose with convection to the photosphere, and finally escaped into space. It crossed the gap to Earth and slid through our air, where shorter blue wavelengths scattered more and longer red wavelengths passed through, coloring the sky. Along the way, the Sun's fields shaped its outer atmosphere. Granules boiled, sunspots grew and faded, loops arched and fell, and at times, the corona let go of a great cloud. We are learning to read these signs with light our eyes cannot see, and with models that tie surface patterns to deep causes. To see why there is light to send at all, we step one level deeper to the engine that makes that energy in the first place. The energy that holds the Sun steady comes from a tiny bit of mass turning into pure energy. Einstein's E equals mc squared tells us that even a small loss of mass yields huge power because the speed of light squared is immense. In the core, 4 hydrogen nuclei fuse into one helium-4 nucleus. The helium weighs slightly less than the 4 protons that made it, and the missing mass becomes energy that moves outward as light and heat. Every second, the Sun converts millions of tons of mass this way. Imagine a few million cars turned into light each second. That steady conversion starts each photon on its long walk, keeps pressure pushing back against gravity, and, 8 minutes after the last step at the surface, paints the morning sky you see. A photon, the smallest packet of light, does not stream straight from the core to space. The glow we see is the last step of a long escape. Deep down, Where fusion happens, the gas is so dense that a newborn photon can barely travel before it is absorbed and re-emitted by another particle. Its journey is a random walk, like trying to cross a crowded room where you bump shoulders every few steps and must change direction. Sometimes the photon goes forward, sometimes sideways, and sometimes it ends up heading back toward where it came from. Over countless collisions, its energy also changes, stepping down from fierce gamma rays to X-rays and finally to visible and infrared light as it nears the surface. The mean free path, the average distance a photon can go between hits, might be only centimeters in the deep interior, so a straight line is rare and patience is everything. The core occupies only about a quarter of the Sun's radius, yet it holds a large share of the Sun's mass. That weight squeezes the plasma hot, ionized gas into a state far denser than iron. Temperatures in the core are many millions of degrees, high enough that electrons are stripped from atoms and the particles move fast. In such a crush, the photon's steps are tiny and chaotic. Think of Brownian motion, the jitter of dust motes in a sunbeam caused by countless unseen hits from air molecules. The photon's path is like that, only more crowded and much hotter. Because the core is so opaque, most of the energy there is carried outward, not by bulk motion, but by radiation slowly leaking through many, many handoffs. Light cannot show us directly what lies below the visible surface, so scientists use other sensors. One is helioseismology, the study of waves that ripple across the Sun's surface. The Sun rings with many tones at once, driven by sound waves that bounce through its interior and push the surface up and down by tiny amounts less than the width of a human hair. By measuring these vibrations, researchers inferred temperature, density, and flow patterns deep inside. Some waves are pressure waves, like sound in air. Others are gravity waves that move more easily in deeper, stable layers. Together, they form a song we can analyze to chart the inside of a star. Another sense comes from neutrinos, ghost-like particles created in fusion. Neutrinos barely interact with matter, so they leave the Sun's core in a couple of seconds and then cross space almost without noticing anything in their way. They reach Earth in about 8 minutes, the same light travel time from the Sun, once photons are free at the surface. For years, detectors found fewer solar neutrinos than theory predicted. The puzzle eased when experiments showed that neutrinos change flavor in flight from electron type to muon or tau type, so early detectors were only counting part of the stream. That result confirmed both neutrino physics and the basic picture of fusion in the Sun's core. As energy wanders outward, it enters the radiative zone, a broad layer stretching from the edge of the core to roughly 70% of the Sun's radius. Here, temperature and density fall with height, yet the material is still opaque enough that radiation remains the main way energy steps forward. The random walk continues, but the average steps grow a little longer. Even a short slab of this hot plasma can block light better than a great depth of water on Earth. To make sense of such conditions, astronomers use the standard solar model, a set of equations that balance gravity's inward pull with pressure's outward push and track how energy moves through opaque matter. Laboratory data on how different elements absorb and scatter light at different temperatures and densities feed these equations. The result is a map of opacity, or how resistant the material is to radiation, and a prediction of where radiation can carry the load and where it fails. Near the top of the radiative zone lies a thin yet important boundary called the tachocline. Here the Sun's rotation changes character. The layers below rotate more like a solid body, while the layers above slide at different speeds with latitude a pattern called differential rotation. The equator laps the poles. A full turn near the equator takes a few weeks, while near the poles, it takes several more. That sheer neighboring layers moving at different rates helps wind up and amplify magnetic fields. Many researchers think the tachocline is a key seat of the solar dynamo, the process that maintains the sun's global magnetic field and seeds the active regions that later show up as sunspots and flares. We cannot photograph the tachocline directly, but its fingerprints appear in the rhythms of surface magnetism and in the way spots migrate in latitude over the 11-year cycle. Above the tachocline, conditions tip in favor of motion rather than radiation. The convective zone begins and fills the outer third of the sun by radius. Here the gas is cooler and more opaque to radiation, so photons do a poor job carrying energy outward. Hot plasma becomes buoyant and rises. Cooler plasma sinks. The pattern is familiar from a pot of water on a stove, though the scale is vast. Near the surface, the tops of these currents show up as bright granules cells, about 1,000 kilometers across, with darker lanes between them. Material rises in the center of a granule, spreads out, cools, and sinks at the edges. Each cell lasts minutes before a new one takes its place. Mixed into this fine texture are larger flow patterns called supergranules, tens of thousands of kilometers wide, and slow, meridional flows that creep from equator toward poles and back at depth, helping transport magnetic fields around the star. The change in transport is a change in texture. In the radiative zone, energy leaks forward by countless small handoffs. In the convective zone, energy rides large-scale flows. Both methods keep the outward pressure that balances gravity. Both leave marks we can see. Granulation patterns tell us about the vigor of the upper flows. The scattering of sunlight by surface vibrations maps deeper flows, including how rotation varies with depth and latitude. Where strong magnetic fields pierce the convective pattern, heat flow is reduced and a dark sunspot forms. Above active regions, loops and arches trace field lines into the outer atmosphere. Limb darkening the way the sun looks dimmer near the edge also confirms that the surface layers cool with height, since we look through shallower, cooler gas toward the limb and through deeper, hotter gas near the center. At the top of the convective zone lies the photosphere, the layer we see as the sun's surface. It is only a few hundred kilometers thick, yet it marks a clear boundary. Below, light is trapped and bounced. At and above this layer, light can escape without being immediately reabsorbed. Temperatures here are on the order of a few thousand degrees Celsius, hot enough to dazzle, cool enough that atoms can grab and release light in familiar ways. The photosphere's spectrum looks close to a warm black body curve but carries fine absorption lines where atoms in the gas have removed specific colors. By reading those lines, astronomers measure composition, mostly hydrogen and helium by mass, with small traces of heavier elements like oxygen, carbon, and iron. Our photon, after ages of random walking inside, finally breaks free here and shoots into space at light speed. About 8 minutes later, it can warm a leaf, power a solar panel, or scatter through air to paint a morning sky red at sunset or blue at noon, depending on the path through the atmosphere. Above the photosphere sit the chromosphere, the transition region, and the corona layers, where magnetic fields dominate and temperatures climb again to the million-degree range. Waves and magnetic reconnection add energy there, and the gas thins to the point that it no longer glows like a surface, but shines in specific ultraviolet and X-ray lines. The outermost layer feeds the solar wind, a flow of charged particles that escapes into space along open field lines. Though thin, this outer atmosphere couples the Sun to the rest of the solar system. When magnetic loops above active regions snap and reconnect, they can launch bursts of radiation and even large clouds of plasma coronal mass ejections that later rattle Earth's magnetic field. This steady flow of energy keeps the Sun in balance, but the star does not stay unchanged. Fusion turns hydrogen into helium in the core. Over time, that change alters the core's structure. Helium ash builds up. Helium requires higher temperatures to fuse than the Sun can manage today. So at first, it does not burn. It simply collects, making the core denser. With less hydrogen left to fuse in the very center, gravity pulls the core a bit tighter. When the core shrinks, it heats up, and that extra heat makes hydrogen fusion run faster in a shell around the center. The star shines a little brighter. Over billions of years, this slow feedback has raised the Sun's energy output compared with its youth. Models suggest a gentle increase over geologic time. One reason Earth's climate history also depends on greenhouse gases, ice, oceans, and clouds to keep conditions steady as the star brightens. The shift affects the layers above. A hotter, denser center sends out more energetic photons, which interact more strongly with the material in the radiative zone. That increases opacity, the resistance to the flow of radiation, so photons can spend even longer there than before. The outer convective zone responds by expanding slightly, because convection becomes the easier way to carry the extra energy toward the surface. None of this is violent in the near term. For us, it means slow changes we read with models and helioseismic maps rather than with a quick glance at the sky. The Sun remains stable because of hydrostatic equilibrium. Gravity pulling inward is matched by pressure pushing outward at every depth. Projecting forward, the fuel supply tells the rest of the story. In roughly 5 billion years, the core will hold so much helium and so little central hydrogen that the Sun can no longer support itself in the same way. Gravity will pull the inert helium core tighter, heating it further, while hydrogen fusion continues in a shell around the core. That change swells the outer layers. The Sun grows into a red giant, its surface cooler and far larger, its brightness much higher. The inner planets move into a harsher environment. Mercury and Venus are almost certainly lost, and Earth's fate depends on details of mass loss and orbit changes. Tides with the swollen star and drag in the extended atmosphere may pull Earth inward. On the other hand, the Sun will shed mass in winds, which lets orbits move outward. The balance of these effects sets the final outcome. Inside the contracting core, the temperature eventually climbs high enough to ignite helium fusion in a brief, dramatic episode called a helium flash in low-mass stars like the Sunday. After that, the star settles for a time into fusing helium into carbon and oxygen in the core, with shells of hydrogen and helium burning at different radii. Later, the star enters an asymptotic giant branch phase with pulses and strong winds that lift material into space. Slow, dense outflows carry carbon, oxygen, and other elements back into the interstellar medium, the raw stuff of future clouds and planets. The outer layers drift away and glow under the star's ultraviolet light, forming a planetary nebula misnamed from early telescope views, but beautiful shells around the center. What remains is a white dwarf, a hot, Earth-sized ember, made mostly of carbon and oxygen, supported not by fusion, but by the pressure of electrons packed tightly together. Without fusion to feed it, the white dwarf cools and dims over very long times, a quiet remnant of a long, steady life. Seen from the ground we stand on, the chain is simple, even if the physics is rich. mass becomes energy in the core through fusion. Energy moves outward first by a patient random walk and then by rolling currents. Magnetic fields, built and braided by moving plasma and rotational shear, shape the surface and the outer atmosphere. Light escapes at the photosphere and fills space. Neutrinos race ahead, telling us almost in real time that fusion is still on. Over deep time, the fuel mix changes, the brightness climbs, and the star's balance points drift. Evidence for this whole picture comes from many lines at once. The spectrum of the photosphere that reveals composition and temperature, heliosysmic modes that map the inside, neutrino counts that confirm fusion rates, and spacecraft images that show the changing outer layers across many kinds of light. Small details tie these layers together. The granulation pattern we see in high-resolution images is the top skin of the convective engine that brings heat up from below. The fine absorption lines in the spectrum shift slightly as waves move the surface up and down, turning the whole sun into a natural seismograph. The way limb darkening changes with wavelength tells us how temperature drops with height. The drift of sunspots in latitude over an 11-year cycle, often shown as a butterfly diagram, reflects how the dynamo builds and transports magnetic fields. Even the solar wind we feel near Earth carries the imprint of its birth. Faster streams tend to come from open field regions near the poles, while slower wind often ties to the edges of active regions where loops and funnels mingle. The picture that emerges is not a solid ball of gas, but a layered, living engine. Deep inside, quantum tunneling lets protons meet despite electric repulsion, and fusion turns a little mass into light. In the middle, photons trade energy in a thick fog of particles. In the outer third, hot plasma overturns like boiling water and stamps a cellular pattern on the surface. Above that, magnetism takes over and sculpts loops, jets, and a halo so hot it defies simple expectations. The same motions that build those fields also wind and unwind them over years, setting the pace of the sun's activity. Tracing a single photon from core to eye ties the layers together from reactions in the core to granules at the surface, and, over time, to the slow change written in helium building at the center. Much of what happens inside the sun stays hidden, yet its reach is not subtle. The fields anchored in that churning surface rise, reconnect, and drive the solar wind, flares, and coronal mass ejections. Their strength waxes and wanes with a real, measured cycle. So the star's rhythm shapes the space around Earth, the air above us, and at times, our tools and plans. This is not astrology. It is astronomy, linking effects to causes. The cause is the sun's magnetic cycle. The effects land on machinery, weather at the margins, wildlife that reads light and magnetism, and very slightly on us. The sun is our main source of energy, so some influence is expected. What is easy to miss is that the influence changes over time. From the ground, the sun looks steady. It rises, sets, and seems the same from day to day. That calm look is a trick of distance. The sun is a hot ocean of plasma, always moving. Magnetic fields knot and unknot. Bright flares flash. Dark sunspots grow and fade. Clouds of charged gas, coronal mass ejections or CMEs, lift away from the outer atmosphere and race into space. Even the corona, the thin halo around the sun, sits at temperatures far higher than the visible surface below it. The activity rises and falls in a repeating pattern. About every 11 years, the sun swings from a quiet phase, called solar minimum, to a busy phase, called solar maximum, and then back again. During maximum, dark spots are common, flares are much more frequent, and CMEs can fire off more than once in a day. During minimum, weeks can pass with almost no spots and few large bursts. This 11-year rhythm is known as the Schwabe cycle. There is a longer beat on top of that. Every 2 Schwabe cycles, about 22 years, the Sun's global magnetic field flips and returns. North and south swap places and then swap back. This is the Hale cycle, a magnetic metronome built into the star. The flip does not make the Sun brighter or dimmer by itself, but it is tied to how and where sunspots form and to the timing of the busiest years. We do not yet know why the cycle lasts about 11 years instead of 5 or 15. The engine is magnetic, driven by the way moving, conducting plasma and rotation build and twist field lines. Some have noticed that Jupiter's orbital period is also near 11 years and asked whether the giant planet's pull might help set the pace. The match in timing may be a coincidence. Jupiter's gravity does tug on the Sun, but it does not explain the cycle's shifts in strength or length from one round to the next. The better answer likely lies inside the Sun's own flows and the shear near the layer that separates radiative and convective zones. Where the cycle's effects are most obvious is in space. Satellites and stations sit inside the Sun's changing wind. When active regions produce flares and CMEs, streams of particles and knots of magnetic fields sweep past Earth. We call the result a geomagnetic storm when it rattles our planet's magnetic field. Space weather centers watch the Sun in many wavelengths, track the solar wind, and can often warn of incoming disturbances days in advance. That time lets astronauts shelter from higher radiation and gives satellite operators a chance to put sensitive systems into safe modes. Radiation and magnetic field changes do more than trip electronics. They also heat the top of the atmosphere. Heated air expands upward. Even at high altitudes, there is still a trace of gas, thin but not zero. During quiet times, satellites in low Earth orbit need occasional boosts to make up for tiny drag. During strong storms, the drag can jump, and spacecraft may need frequent maneuvers to stay aloft. Some storms have brought satellites down faster than planned. After major events, tracking networks have had to update the paths of hundreds of objects because the puffed-up atmosphere changed their orbits. The ionosphere, the layer where atoms are split into ions and electrons, also changes during storms. Extra charged particles bend and smear radio waves. GPS signals that usually place you within a meter can drift to 10 meters or more when the ionosphere is disturbed. Power grids on the ground prepare for extra currents induced in long wires. Airlines may alter high-latitude routes to avoid higher radiation levels and radio blackouts. Not every effect is a problem. Amateur radio operators and some pilots use the energized ionosphere to bounce signals over longer distances. But for most of us, the short version is simple. During solar maximum, technology is a little less steady. There is beauty in the restless sky as well. When fast particles ride down Earth's magnetic field lines and strike the thin air near the poles, they make aurora. During busy years in the solar cycle, auroras become more common and creep farther from the poles. Places like Canada, Scandinavia, and Alaska see more nights with moving curtains and arcs of light. For many viewers, that is the first sign that the Sun's mood has changed. The cycle touches climate and living things in small ways. When the Sun is quiet, the solar wind's shield, the heliosphere, relaxes slightly, and more high-energy cosmic rays from the galaxy can reach the top of our atmosphere. When the Sun is active, the shield is stronger, and fewer cosmic rays get in. Some researchers have asked whether cosmic rays help seed cloud droplets by creating tiny charged clusters in the air. If that link exists, more cosmic rays could mean a bit more low cloud and small shifts in sunlight reaching the ground. The jury is still out. The idea is interesting and under study, not settled fact. There is clearer evidence that space weather can nudge temperatures at the edges of the atmosphere, and that surface air patterns can respond in small, temporary ways. During active times, added energy in the upper air can slightly alter winds and waves that move downward through the atmosphere. The overall change at ground level is modest, on the order of tenths of a degree, and fades as conditions calm. Small, however, is not the same as zero. Many species use temperature as a cue. A slight shift in a season's start can move behavior by days. Birds are one example. In warm springs, some birds tend to lay earlier. One long-term study of blue tits in Europe even found a link between laying dates and the number of sunspots recorded, although the path from sunspot counts to nest timing is not obvious. The animals are not checking the sun. They are reading local cues like light and warmth. If the sun's cycle nudges those cues, the timing can move. Other species notice the magnetic field itself. Homing pigeons and migratory animals that sense magnetism may adjust routes or timing when the field is disturbed, or when the background solar wind is stronger or weaker. Humans are not outside these patterns, but the effects are faint and easy to confuse with other causes. Studies that look for links between solar activity and health must use very large groups to find a signal at all. One set of medical records from a European population showed small peaks in certain diagnoses in the years just after solar maximum. Another analysis noted tiny rises in basic body measures: temperature, pulse, blood pressure, breathing in a subject, tracked through changing solar conditions. Results like these are not proof of a direct cause. They point to correlations that invite careful follow-up. There are also studies that look backward, asking whether the solar cycle phase at birth is tied to later outcomes. One survey of hundreds of thousands of records found a small increase in certain mental health diagnoses among people born during periods of higher solar activity. Again, the signal was weak. Many influences shape a life, and separating them is hard. The most honest reading is that if the solar cycle touches human health or behavior, it does so in tiny ways, and only careful statistics can find the pattern. It helps to keep scale in mind. The sun dominates our climate by setting the baseline energy Earth receives, but the 11-year cycle adds only a gentle tremor on top of that. Weather and climate are driven by many factors: ocean currents, volcanic dust, greenhouse gases, ice and land feedbacks, and more. The sun's cycle is one piece, not the master switch. Still, because our tools, networks, and decisions are so sensitive, small solar changes can matter for operations and timing, even if they do not rewrite the climate. What the cycle does write clearly is a schedule for space weather. Forecast centers update risk levels as active regions turn toward Earth. Satellite makers harden electronics and add safe mode plans. Power utilities practice for induced currents and install protective devices. Airlines adjust communication plans for polar routes. These steps reduce the chance that a single storm will cause large problems. During the build-up to a solar maximum, the pace of these precautions increases. That is where we are now, with activity high around 2025. The idea that a star's cycle might nudge creativity or adaptability in people is more speculative. Some researchers have suggested that stressful environments of any kind can select for flexible thinking. If higher solar activity adds a tiny layer of stress through sleep disruption, tech glitches, or small weather shifts, the result might be a slight rise in creative responses in some groups. This is an interesting idea, not a settled result. When we reach back tens of thousands of years to imagine links between ancient solar conditions and human brain changes, we move from data into storytelling. It is fine to wonder, and wise to mark the line between what we know and what we are still testing. While the cycle's causes remain a puzzle, the need to measure the sun up close is obvious. We learn the most when we can watch cause and effect at the source, where magnetic fields twist, where the solar wind forms, and where the corona is heated. In the past decade, 2 missions have taken us closer to that source than ever before. One skims through the inner solar wind on a path that dips deep into the sun's outer atmosphere. The other flies in a tilted orbit that lets it look at the poles and trace the outflow of particles and fields from high latitudes. The first mission is designed to taste the solar wind where it is still forming. It carries instruments that count particles, measure their speeds and temperatures, and map the magnetic field around them. By sampling the wind at different distances from the sun, it can tell whether bursts seen near Earth started as slow puffs that were later pushed and merged, or as fast streams right from the start. It can test whether waves and turbulence in the wind are strong enough to heat the corona and drive the flow outward. The second mission is built to see. It has telescopes that image the visible surface, the chromosphere, and the corona in many wavelengths. It also carries a coronagraph, a device that blocks the bright disk and reveals faint structures around it, much like an artificial eclipse. Because of its path, it can view regions that are hard to see from Earth, including the poles, which may hold clues to the global magnetic flip every 11 years. Together, the 2 missions let us link local samples of the wind to global pictures of the sun's face and halo. These spacecraft fly through rough weather by design. They endure heat shields that glow, and they navigate through changing fields and dust. Onboard computers make quick choices to protect the instruments while keeping the science going. Each close pass adds detail to our map of the sun's near environment. Each distant view adds context to what the close probe feels. Step by step, we are learning where the solar wind is born, how small jets and waves feed it, and how magnetic knots trigger flares and CMEs that can reach us. Better maps and models lead to better forecasts. If we can tell when a tangle of fields is likely to snap, when a slow wind will be overtaken by a fast one, or when a new active region is turning to face Earth, we can give earlier warnings. That helps keep astronauts safe, satellites healthy, and grids stable. It also lets us plan science. When a flare or CME lifts off, telescopes across the spectrum can focus on the event, and in-situ sensors can watch for the arriving shock. The result is a full chain of evidence from source to impact. The picture that emerges is not one of a calm lamp in the sky, nor of a wild, random blaze. It is a living engine with patterns. There are cycles, flips, bursts, and lulls. There are parts we can predict and parts we still chase. The 11-year rhythm grows and fades, bringing more auroras, more radio noise, more drag on satellites, and, at the edges, small nudges to weather and biology. Most days the sun simply powers life. On some days, it reminds us that we live next to a star. To move from hints to answers, we keep watching, and we keep flying closer. These new missions are more than photographs and numbers. They are our hands held near the fire, feeling the wind where it starts. We go to such lengths because seeing the source tells us what to expect at home, and because the sun's workings are part of our story. The first close-in explorer that makes this possible is NASA's Parker Solar Probe. Parker is our closest visitor to a star. Announced in 2009 and launched in 2018 on a heavy-lift rocket, It has used a careful series of Venus flybys to fall inward, step by step, toward the Sunday. Each pass by that cloud-wrapped world steals a little orbital speed and tightens the path. By late December 2024, the probe swept through its closest passage so far, about 6.16 million kilometers above the visible surface, flying inside the corona, the Sun's hot, thin outer atmosphere. At that distance, the sunlight is brutal, like hundreds of suns stacked together, and the surrounding heat can climb well above 1,000 degrees Celsius. Ordinary spacecraft parts would fail. Parker survives by hiding behind an 1 centimeter thick carbon composite heat shield with a bright white face that reflects light and blocks heat. The spacecraft keeps that shield pointed at the sun at all times, holding its instruments in the shade as it works. Flying that close means the probe must take care of itself. For long stretches, it cannot turn to face Earth with its antenna without exposing parts of the craft to direct sunlight. So it stores what it measures, manages its own sensors, and keeps its system safe while out of contact. When it swings back to a view where Earth is reachable, it points its antenna and sends home the files it has collected from the near-Sun environment. The rhythm is simple. Dip in close, feel the wind and fields, then turn outward and report. Europe's solar orbiter works on the same problem from farther out. Development began in the early 2010 seconds, and the spacecraft launched in 2020, also using a series of planetary assists to shape its path. It reaches close approaches roughly every 6 months at a distance of about 43 million kilometers. Even there, sunlight is more than 10 times stronger than at Earth, and surfaces can reach temperatures around 500 degrees Celsius. Solar Orbiter carries a layered metal heat shield to protect its body and instruments while it looks at the Sunday. The job is still harsh, but the distance allows it to point telescopes toward the bright disk and take images in visible and ultraviolet light. That view lets it follow the same region on the Sun for days and watch storms build. Both missions share a set of core questions. Why is the corona millions of degrees while the visible surface below it is much cooler? Where and how does the solar wind start? And what heats and accelerates it? How do small magnetic knots grow into major active regions? When do loops of magnetic field reconnect and explode as flares? When do those explosions lift a huge bubble of charged gas into space? A coronal mass ejection, or CME. And how does that bubble evolve on its way to Earth? A CME is a massive cloud of plasma threaded with magnetic field lines. When one of these clouds reaches our planet, it can push and twist Earth's magnetic field, a disturbance we call a geomagnetic storm. The strongest reminder of what a storm can do came in the late summer of 1859. Over several days, large sunspot groups grew on the Sunday. Observers recorded unusual auroras far from the poles, a sign that space weather was already active. On September 1, 2 astronomers watching the Sun in daylight saw a sudden bright patch, a flare in roughly the same region. Within hours, a powerful CME reached Earth much faster than most. One likely reason for the speed is that an earlier ejection had swept the path clean, leaving less solar wind material to slow the next wave. When the big cloud arrived, auroras surged to low latitudes across both hemispheres. Reports describe miners waking under green skies in the Rocky Mountains, readers in the northeastern United States making out newspaper print at night, and lights seen as far south as the Caribbean and near the equator. The beauty came with trouble. Telegraph systems across Europe and North America sparked and failed. Operators felt shocks at their keys. Some found that even with their batteries disconnected, currents induced by the storm still carried dots and dashes along the wires. Earth's magnetic field had been pressed close to the atmosphere, and long conductors acted like antennas for the changing fields. The technology of the day was simple enough to survive the event, if not gracefully. More than a century later, large storms still cause problems, though most are far weaker than the 1859 event. In March 1989, a storm disrupted satellites and radio links and led to a power outage across parts of Quebec, when currents induced in long transmission lines and transformers pushed systems beyond designed limits. Operators restored service, and permanent damage was limited. But the message was clear. Modern life draws strength from long, delicate networks. Those networks are now tied to a star. If a storm the size of the 1859 blast were to arrive today, the stakes would be higher. Satellites carry sensitive electronics. Navigation, timing, and communication rely on signals that pass through the ionosphere, the electrical shell around Earth that storms disturb. Power grids connect cities with high-voltage lines that stretch across long distances. A severe space weather event could drive extra currents through those lines and saturate transformers. These machines are not easy to replace. They are large, custom-built, and take time to manufacture. A single failure can be handled. Many on the same continent would be hard. Without power, supply chains stumble, fuel pumps stop, freezers warm, and digital payments go offline. Utilities and agencies plan for these risks, and most storms pass with little harm. But the risk exists because the systems are so connected. Some studies have tried to put a price on an extreme event, with large numbers offered for potential damages and long recovery times if many critical parts failed at once. It is wise to treat such estimates with caution. They try to model rare events with many unknowns. The practical lesson is simpler and steadier. Hardening key equipment, building surge protection, designing safe modes for satellites, and writing response plans make networks more resilient. Warning time also matters. A fast CME can cover the Sun-Earth distance in less than a day, yet most take longer. In 2012, a strong storm crossed Earth's orbit when our planet was just 9 days farther along, so it missed us. Near misses are reminders, not guarantees. Better forecasting can turn a close call into a drill rather than a crisis. That is why these missions fly. Parker Solar Probe works inside the corona, where the solar wind is young. It cannot point a camera at the sun's face. From that close, no detector could stare at that glare and heal. But it has instruments that count. Particles read their energies and directions and measure the magnetic field threading through them. Those in situ measurements tell us whether the wind comes off the surface smoothly like steam or in little jets, and whether waves and turbulence in the plasma are strong enough to heat and accelerate it. Parker also samples the fine structure of switchbacks, sharp kinks in the magnetic field thought to be tied to how energy moves through the near-Sun environment. Solar Orbiter, farther out, carries both particle detectors and telescopes. It can take images in visible light and extreme ultraviolet, map the magnetic field at the surface, and use a coronagraph, an artificial eclipse, to see faint structures near the bright disk. Because of its orbit, it can stare at a single active region for days, long enough to watch a loop rise, twist, and sometimes let go. Over time, the mission will tilt its path to look down on the sun's poles, areas that control the global field but are hard to view from Earth. That polar view matters for understanding the 22-year Hale cycle and how the field flips. Both missions study reconnection, the process where magnetic field lines break and form new connections, releasing stored energy. In small bursts, reconnection might power jets and waves that feed the wind. In larger regions, it fuels flares and helps launch CMEs. sampling particles and fields where reconnection is happening, and watching the same region in images at the same time gives a direct link between cause and effect. The pairing is the point. One mission tastes the soup, the other watches it boil. Alongside the science, the engineering is a quiet achievement. Parker's heat shield faces temperatures that would melt aluminum, yet behind it, the main body stays near room conditions. The craft must hold its aim with high precision so that nothing peeks around the shield's edge. Its autonomy is not a luxury. When the sun fills the sky, there is no time to ask Earth for advice. Solar Orbiter faces a different challenge. It must protect itself while opening windows to observe. Doors in the heat shield swing to let telescopes look and then close again. Radiators spill heat to the cold of space while the side facing the sun bakes. Star trackers, gyros, and software keep the line of sight steady while the whole platform endures uneven heating. What these missions learn feeds directly into forecasting. If we can recognize patterns in the near-sun wind that always precede a shock, we can give earlier alerts to satellites and stations downrange. If images show that a CME is narrow and off to the side, operators can relax. If the core of a CME is aimed squarely at Earth and carries a magnetic field aligned in a way known to couple strongly with our own field, agencies can prepare for stronger effects. Minutes and hours matter. A few extra hours can move a satellite out of a risky mode, adjust a grid, or reroute a polar flight. Days of warning can stage equipment and people. The Parker and Solar Orbiter datasets also help us test long-standing puzzles. One is the coronal heating problem. What keeps the corona so hot compared to the surface below? Two broad ideas share the stage. One points to countless tiny magnetic reconnection events, sometimes called nanoflares, that happen all the time, too small to see individually, but powerful in total. The other points to waves that carry energy from lower layers upward and then break or dissipate in the corona. In reality, both may contribute, with the balance changing by place and time. Measurements of particle distributions, wave activity, and magnetic structure close to the source help choose between competing models. Another question concerns the birth of the solar wind. Images show jets and plumes from coronal holes, regions where the field opens into space, yet the detailed path from a loop at the surface to a breeze at Earth is still being mapped. Parker's fly-throughs at different distances let us see how the wind's speed, density, and temperature evolve, and how the switchbacks relax or persist. Solar Orbiter's long looks show how a patch on the surface changes while Parker samples the outflow from that region later on. Linking the two is like matching the pattern of ripples far from a shore to the stones thrown in earlier. Storms large enough to rival 1,859 are rare, but not impossible. Their frequency is uncertain because our direct measurements are young and our proxies, tree rings, ice cores, and old reports are indirect. Planning assumes they will come again. Power companies add monitors and procedures. Satellite makers design for radiation spikes and include safe mode scripts to lower risk during predicted storms. Agencies share alerts across borders because space weather ignores them. Schools add aurora warnings to community notices, and many people step outside at night to look up when forecasts are strong. The same cycle that increases risk also brings more nights of moving light. The long view puts the present in context. We live next to a variable star whose surface and atmosphere are shaped by magnetic fields born from heat, rotation, and flows inside. Those fields rise, twist, reconnect, and sometimes throw clouds into space. Most days pass without any sign beyond the quiet glow of noon. Some days bring extra drag to satellites, extra currents to long wires, and changing radio paths around the poles. A few days in a lifetime will bring storms that we remember. The aim of flying behind a heat shield and staring through a moving slit is practical and modest. Learn enough about the source to make those few days safer and more predictable. Parker's next close sweeps will push boundaries again, repeating a pattern that has guided space exploration for decades. Go a little closer, measure a little better, compare notes, refine the model, and try again. Solar Orbiter's continuing passes will add views of the poles and longer baselines for watching regions age. Together they make a pair one up close, one pulled back that can turn a bright, featureless glare into a layered story. The closer we get to the source, the more steady our footing becomes here at home. A storm moving across interplanetary space is not a single blow. It is a structure that changes as it travels, pulling in slower wind, piling up shock fronts, and rotating its embedded field. By sampling at several distances and looking from several angles, we learn how that change unfolds. The lesson returns to the power grid and the cockpit and the satellite bay. Small steps in understanding give small steps in prevention. That is enough. Stars do not yield all at once. They give us patterns, and we learn to read them. Taken together, the two missions are different by design. Parker is a sampler. It plunges into the corona, cannot stare at the disk, and brings back local truth. How many particles? How fast? In what directions? With what magnetic field wrapped around them? Solar Orbiter is an observer that can also taste the wind where it flies. It takes images, watches the same place for days, blocks the sun to see faint halos, and builds a movie of change. One mission tells us what the wind feels like. The other shows us where it comes from. Their overlap is the strength. By pairing touch with sight, we can link a twist on the surface to a switchback in the wind, a flare in one channel to a shock at a probe, and a lifted filament to a CME that brushes Earth days later, turning a steady-looking star into a system we can track and, with practice, forecast. And the payoffs are already showing. In late December 2024, Parker swept to within about 6.16 million kilometers of the Sun's surface, and, on that dive, set a speed record for a human-made object racing near 700,000 kilometers per hour. From these close passes, the probe has returned measurements that tie the Sun's magnetic field to the flow of the solar wind in concrete ways. It has seen field lines bend and sweep through the corona like trail switchbacks, briefly pointing back toward the Sun and then away again, and shown that such bends can boost outflow speeds by hundreds of thousands of kilometers per hour. Parker has also found signs of a dust-poor inner zone within a few million kilometers, likely where fragile grains are heated and vaporized by intense radiation, leaving the near-Sun region unusually clear. Solar Orbiter adds detail from a safer distance. Its first high-resolution images revealed tiny, bright flashes dotting the surface, and lower atmosphere researchers nicknamed them campfires. These events are small compared with classic flares, but they are numerous, and they cluster where magnetic fields are tangled. The spacecraft captured the closest full disk and close-up views yet from tens of millions of kilometers away, and it pairs those images with direct sampling of particles along its orbit. That mix helps separate types of space weather and shows how small disturbances grow into larger structures as they move outward. Another line of discovery asks a different kind of question. If sound could travel in space, what would the Sun sound like? In a vacuum, there is no air to carry pressure waves, so the true answer is silence. But instruments can measure waves in plasma fluctuations in density, pressure, and electric and magnetic fields, and those signals can be translated into audio for our ears. The result is not music, but a map, tones and textures that reflect the behavior of the wind and the corona. Listening in this way turns complex data into something we can recognize. And those patterns point toward two long-standing puzzles: why the solar wind accelerates so efficiently and why the corona is so hot. If space did carry sound, the sun would be loud even from Earth's distance. The star's power output is enormous, and the constant churning of its surface and atmosphere would create a broad, steady roar. Translated to a human scale, researchers often describe a deep electrical hum, more felt than heard. The numbers put edges on the idea. A typical rock concert measures around 110 decibels near the speakers, loud enough to damage hearing without protection. Near the sun, where the air would be far denser and more energized if it existed at all, modeled levels climb far beyond anything Earth's atmosphere could carry. Our air imposes a practical ceiling near 190 decibels. Above that, the wave breaks, and the medium cannot hold a larger pressure swing. Close to the solar surface, estimated sound pressures exceed that cap by large factors. The point is not the exact decibel figure, but the scale. The sun's motion is vigorous. Volume, however, hides detail. Far away, many of the sun's signals blur together. To hear the differences, we imagine moving inward. The steady hum gives way to structure rises and falls, hisses and chirps that trace specific processes. One of the first textures would be the solar wind itself, a restless, gusting rush. The wind is a continuous stream of charged particles that flows from the corona into space. Early expectations were that this outflow would be a simple release from the hot surface, but measurements showed something subtler. Near the sun, particle speeds are relatively modest. Farther out, they are typically hundreds of kilometers per second, and often supersonic for that environment. Somewhere above the surface, the gas gains a powerful push. The identity of that somewhere and the exact push remain core questions. Heat adds a second enigma. The visible surface of the sun sits around a few thousand degrees Celsius. Climb just above it into the corona, and the temperature jumps by orders of magnitude to the million-degree range. A thin, tenuous atmosphere above a cooler surface should not be hotter, yet it is. Energy must be deposited there, and a mechanism must carry it upward. Theories point to magnetic fields and waves in the plasma, but the balance is still under study. Listening to the corona through translated signals gives clues to which processes are active and where. Crossing the boundary where the wind decouples from the sun's magnetic grip, often called the Alfvén surface, the region where the outflow outruns certain waves tied to the magnetic field, you would hear sharper textures. One is a bright, glassy hiss linked to Langmuir waves. In plasma, electrons can oscillate collectively at a natural frequency. That motion creates electrostatic waves that instruments can detect. When streams of electrons pass through the background plasma, as they often do in the wind, they can excite these waves and make them sing. On Earth, the nearest analog might be the fine whistle of a kettle, though the physics is different. In space, the kettle is a beam of particles gliding along a magnetic funnel. Those funnels root in the surface pattern we saw earlier. The sun's visible face is tiled with granules, the tops of convection cells where hot plasma rises in bright centers and cooler plasma sinks along darker edges. Magnetic fields concentrate in the lanes between granules. There, the fields can open upward like threads into space. Along those open lines, particles escape more easily, feeding the fast component of the solar wind. The rising and sinking below, the tangle and release above, and the beams along open fields blend into a layered soundscape. When translated to audio, the mixed waves produce dispersive effects, higher frequency parts that travel faster, lower frequency parts that lag, creating sweeping chirps as packets pass one another and merge into a broader tone farther out. A different family of tones carries a hint at sudden energy release. These are Whistler mode waves. On Earth, lightning can trigger them. A bolt creates a disturbance that races along magnetic field lines, and sensitive receivers far away pick up a falling whistle as the signal disperses. In space, many processes can drive whistlers, but they are often linked to sharp changes in electric and magnetic fields. When instruments near the sun translate their data, the whistler component is not sparse or occasional. It is dense, a near-constant chorus. That suggests frequent small events across the corona, not just the rare big flare. One candidate for those events is magnetic reconnection. In a plasma, magnetic field lines can be carried and bent by the moving gas. Where oppositely directed lines are pushed together, the configuration can become unstable and rearrange into a lower energy shape. That rearrangement, the reconnection, converts stored magnetic energy into heat, light, and motion. On large scales, reconnection powers big flares and helps launch coronal mass ejections. On small scales, many tiny reconnection bursts, sometimes called nanoflares, could deposit heat all across the corona. If they happen often enough and nearly everywhere, they could explain the high temperature and help accelerate the wind. This is a working theory. Evidence has grown as instruments have improved, but researchers are still testing whether the observed small flashes match the predicted properties and whether they are numerous enough to carry the load. Parker's measurements bring this picture closer to the source. The probe has flown through regions where the magnetic field suddenly kinks and reverses features, nicknamed switchbacks. In those zones, particle speeds spike, wave power rises, and the field geometry suggests a release of tension. These are the local signatures you would expect if many small reconnection events were popping off, or if strong waves were breaking and dumping energy into particles. By mapping how often these features occur and how they change with distance, Parker puts numbers to ideas that were once only models. Solar Orbiter provides the broader view needed to connect cause and effect. Its telescopes can watch an active region for days, catching faint brightenings and tracking loops as they twist and reform. Coronagraph images reveal faint outflows just above the limb, plumes and jets that might mark the start of larger structures. When the orbiter's particle detectors then feel a change in the wind hours or days later, the two can be tied together. That pairing, seeing a small brightening and then sampling the outflow tied to it, turns a guess into a chain of evidence. The campfires are a case in point. They dot the surface, like sparks on a grill, too small to count as classic flares, but too frequent to ignore. Their spectra and timing hint at magnetic origins. If each one adds a little heat to the surrounding plasma, and if they are as common as they appear, their collective effect could be large. The same goes for the switchbacks that Parker flies through. If they are snapshots of field lines that have been bent and snapped back, they point to quiet but constant work being done by the magnetic field on the plasma. The dust poor inner zone adds another thread. Many models assumed that dust would thicken steadily toward the sun until radiation pressure balanced gravity and drag. Parker's evidence for a region where dust is rare suggests that grains near the sun are destroyed faster than they are supplied. That matters because dust affects how light is scattered and absorbed in the inner system, and because evaporating grains add atoms to the plasma, changing how it conducts heat and responds to fields. A cleaner inner region could make the near-sun wind behave differently than expected, altering where waves grow and where they fade. Speed records and temperature shields make headlines, but the quiet achievements are in calibration and patience. Flying within the corona means dealing with a changing environment where dust, fields, and particles all vary with time and position. Instruments must separate true solar signals from the craft's own effects, and teams must stitch together data from many passes into a coherent map. On the imaging side, long exposures at high temperature and brightness demand careful handling so that faint features near the sun can be seen without swamping detectors. Each improvement tightens the link between a flare seen on the limb and a shock felt later in the wind. All of this folds back to practical forecasting. A CME is not just a blob, it is a structured knot of field and plasma that changes as it travels. If its internal magnetic field arrives in a direction that couples strongly with Earth's, especially southward in a certain coordinate system, the storm on our side will be stronger. By sampling CMEs closer to their source and watching their shape as they leave, we can better estimate that orientation and the timing of their arrival. That can turn an uncertain window into a focused warning. The sound translations are more than a novelty. Our ears are good at picking out patterns, regular beats, rising pitches, sudden clicks that can be hard to see in graphs. When scientists convert field and particle data into audio, they often spot features that deserve a closer look. A new kind of burst might show up as a brief chirp. A particular wave mode might make a steady whistle that grows and shrinks with solar rotation. These clues then send analysts back to the numbers to quantify what the ear noticed first. The two missions are still building their archives. Parker continues to tighten its orbit with each Venus flyby, pressing farther into the corona and spending more time in the young wind. Solar Orbiter is shifting its path to improve views of higher latitudes and, in time, the poles. As those datasets grow, the sun's voices become clearer. The low hum of the outflow, the hiss of Langmuir waves in electron beams, the whistles that mark sudden changes, the rustle of tiny brightenings at the footpoints of loops. None of these sounds carries through space to our ears, but each carries meaning when translated. It is possible that the answers will not be singular. The wind may start in different ways, in different places. The corona may be heated by waves in one region and by nanoflares in another, with the balance shifting over the 11-year cycle. The campfires seen by Solar Orbiter may be one face of a broader process that Parker feels as switchbacks. The dust-poor inner zone may expand and contract with activity. The work now is to match times and places, tie a pattern in the audio to a feature in an image, and to a spike in a detector, then repeat until the picture holds steady. As the missions continue, even the simple facts gain depth. The record-setting speed tells us how deep Parker has dropped and how much energy it trades with Venus to get there. The heat shield steady aim tells us about control systems that let science run while the spacecraft protects itself. The campfires tell us that small magnetic events are common, not rare. The dust-poor region tells us that the near-Sun environment is harsher to solids than expected. Together, these facts sketch a sun that is not a smooth furnace, but a layered, restless system where countless small acts add up to global flow. If we could listen directly, the sun would never be quiet. Instead, we listen through proxies, waves in plasma, packets of particles, faint flashes in ultraviolet light. Each is a language. Parker and Solar Orbiter are translators as much as explorers. By turning those languages into forms, we can study plots, images, and even sound. They let us test ideas that once lived only in theory. The mysteries of acceleration and heating may not yield to a single key, but the clues arrive one pass at a time, and patterns begin to rhyme. And the same physics we learn from these clues, how energy moves, how fields shape flows, and how orbits really work, also answers practical questions that seem simple at first glance. It is tempting to think that if we can guide a careful probe around the sun, we could also throw other things toward it. The question returns whenever people discuss hard-to-manage waste on Earth, ordinary plastics and landfill trash, but also the dangerous kinds, nuclear byproducts, biohazards, and long-lived chemical toxins. These materials strain ecosystems and harm nearby communities. For the worst of them, deep rock storage is the current standard, backed by thick steel canisters, glass logs, vitrified waste, and dry casks that shed heat systems designed to last thousands of years. Even so, a final fix sounds appealing. Strap the waste to a rocket and send it into the Sunday. It feels like tossing a stone into a fire. But the space flight we have just learned to do around a star shows why this is not simple at all. The first hurdle is leaving Earth. A payload must reach about 11.2 kilometers per second to escape Earth's gravity escape velocity. Big rockets can do that. But escaping Earth is not the same as falling into the Sunday. When you reach orbit around the Sun, you still have Earth's sideways speed, about 30 kilometers per second. That sideways motion is what keeps Earth and anything launched from it moving around the Sun instead of dropping in. If the Sun's gravity vanished, we would fly straight along that tangent. If our sideways speed vanished, we would fall inward. To send waste into the Sun, you must cancel most of that 30 kilometers per second. That is the real problem. In space, you do not brake with friction. You change velocity with thrust. One option is to fire a rocket opposite your direction of travel until the sideways speed is gone. But the closer you are to the Sun, the faster your orbital speed becomes. So the more you must cancel to dive inward. Mercury circles the Sun at 48 kilometers per second. Pluto at 4.7 kilometers per second. Counterintuitively, it can be more fuel efficient to go outward first, slow down where speeds are lower, and then fall in. All of this runs into the same wall, the rocket equation. Carrying more propellant makes you heavier, and pushing that extra mass takes still more propellant. Even the Saturn V, built to fling humans to the moon, burned on the order of millions of liters of propellant just to reach Earth escape. A break-and-fall mission to the Sun would demand orders of magnitude more, plus tanks, plumbing, engines, guidance, and safety systems. You could launch the waste first and then launch fuel to meet it in orbit, but the total mass you must push still explodes. You do not escape the math. There are gentler tools than brute force. Gravity assists let you trade energy with planets. Most people know the slingshot that speeds probes up, like Voyager racing to the outer system. The same trick can slow you down if you fly past a planet in the right way, approach from behind, pass in front, and leave with less energy while the planet gains a tiny bit. Missions to Mercury, such as Messenger and Bepicolombo, use long chains of flybys because a single burn cannot cancel enough speed. It works, but it takes patience and precision. Bepicolombo launched in 2018 and needs multiple assists from Earth, Venus, and Mercury to arrive in Mercury orbit years later. The path it travels is longer than the distance from Earth to Pluto, even though Mercury is close to the Sun in space. A disposal craft to the Sun would face the same slow spiral. If you do not remove enough speed, you stay in a long, stretched orbit. If you remove too much at the wrong angle, you can get trapped in an unwanted orbit around another body. Each pass must be timed exactly. Each burn must be clean. Even if the trajectory works, the risk case is hard to accept. We are talking about loading nuclear waste, biohazards, or toxic chemicals onto a rocket and lighting the fuse. Modern rockets are reliable by historical standards, but not perfect. Across many years and many flights, even the best families show a small failure rate. With a payload like this, small is not small. A launch mishap could scatter dangerous material over ocean or land. Engineers can design strong containers, double-walled canisters, crushable layers, heat-resistant shells to survive an explosion and an unplanned splashdown. But more protection means more mass, which means bigger rockets, more cost, and still no promise of absolute safety. If the rocket fails on ascent, the very thing you are trying to remove from Earth ends up back on Earth in a harder-to-control form. The budget case is no kinder. A real program would need multiple heavy launches, on-orbit assembly or refueling, long cruise times with constant tracking, and careful navigation. That cost would compete with weather satellites, Earth science missions, climate monitoring, planetary probes, space telescopes, medical research run from orbit, and the infrastructure that keeps space safe for everyone. Each of those missions has clear, broad benefits. In contrast, a throw it into the sun project would remove only a small fraction of the world's waste at very high cost and high public risk. The same funding could harden grids against solar storms, clean waterways, build safer storage for nuclear waste, and develop next-generation recycling and materials. Space is not a shortcut around earthly work. A common follow-up is, if we cannot throw waste into the sun, can we throw it out of the solar system? Strangely, that is less demanding in one way. To be free of the sun from Earth's orbit, you need a speed of about 42.1 kilometers per second relative to the sun, which is roughly 12.1 kilometers per second more than Earth's orbital speed. That push is still large, but it is notably less than canceling the full 30 kilometers per second sideways motion. Electric propulsion ion thrusters can deliver large total changes in speed over long periods with less propellant, but they need power and time. Solar sails can trade momentum with sunlight, but they are fragile and heat-limited near the sunday. Nuclear thermal or nuclear electric rockets could, in theory, help, but they raise a new set of safety and policy questions. And none of these erase launch risk. One bad day on the pad or in the first minutes of flight could cause the very harm the mission was meant to prevent. When the payload is toxic, pretty safe is not safe enough. There are other, often overlooked issues. Planetary protection and space environment rules exist to avoid contaminating other worlds and to keep Earth's neighborhood usable. Filling Earth orbit with heavy disposal flights would add traffic and potential debris. If an upper stage failed and broke apart, it could help seed a cascade of collisions, what's often called a Kessler syndrome, making certain orbits hazardous for years. Even a small increase in debris raises tracking and avoidance costs for everyone. On the ground, communities near launch sites would carry more risk while seeing little of the benefit. Space policy is built on shared resources and shared safety. A disposal program runs against that grain. So why does the idea keep returning? Because the sun feels final. It is easy to imagine that once waste is in the sun, the problem is over. Physics pushes back. The energy you must remove to fall into the sun is large. The rocket equation punishes every extra kilogram. Gravity assists demand years. The risk concentrates at launch, where failure is most likely to happen and where the consequences would land on people and places that did not choose them. When you add up engineering, cost, time, and ethics, the plan does not pass. The better path is less dramatic and more reliable. Use less. Design materials that can be reused many times. Replace persistent toxins where possible. For nuclear waste that remains, use multiple barriers, corrosion-resistant containers, glass or ceramic forms that immobilize radionuclides, geologic media like salt, clay, or deep crystalline rock. That slow water movement and careful monitoring. These systems are built to fail slowly, layer by layer, in ways we can repair. They are not perfect, but they are controllable. When new methods like advanced reactors that can consume some long-lived waste become practical, we can adapt. None of this is as cinematic as a rocket plunging into the Sunday. All of it is safer. A few background details help explain why just cancel 30 kilometers per second is so hard. Velocities in space add and subtract by vector, not by simple sign. You leave Earth on a path that is already moving around the Sunday. Burns are most efficient when made deep in a gravity well, where your speed is high, the Oberth effect. That is why probes light engines at perihelion if they can. But to do that near the Sun, you must first get near the Sun without melting your ship or running out of propellant. Parker Solar Probe cheats with physics we do not have for heavy payloads. A heat shield that keeps instruments in shade, and a slow series of Venus flybys that trade orbital energy over years. Even Parker, which masses less than many cars, cannot stare at the Sun or carry bulky cargo. There is no camera on its nose. Glare and heat would destroy it. That should set expectations for a waste freighter. A note on reference frames also matters. From Earth's point of view, geocentric, a rocket that escapes Earth has done the job. From the Sun's point of view, heliocentric, the same rocket is simply a small object with almost exactly Earth's orbital speed, now moving alongside us on a similar path. To fall inward, you must erase that sideways motion in the heliocentric frame. That is where the big delta V lives. It is not hidden in clever staging or a new fuel. It is baked into the orbital dance that keeps Earth where it is. Risk is not only about explosions. Suppose a disposal mission made it to deep space and then suffered a slow leak. The material might vent and freeze into many small pieces spread over a long path, turning a single, well-contained problem into thousands of hard-to-track ones. Engineers can design containers to avoid that. They can also design re-entry plans that bring a failed payload back into the ocean in one piece. But each, just in case, adds weight and cost, and none can offer a 100% guarantee. On Earth, by contrast, failed containers can be replaced, monitored, and surrounded by more barriers. If a storage gallery floods, pumps can run. If corrosion shows up on a canister, you can repair or overpack it. Control is the difference. All of this can feel like turning away from the sky. It is not. The more we learn about the Sun, the better we become at planning and protection here at home. Parker Solar Probe and Solar Orbiter exist because the Sun's changing wind and magnetic storms can shake our satellites and grids. By sampling particles where the wind is born, and by imaging the fields that let flares snap free, these missions sharpen space weather forecasts. That buys time. Time to put satellites in safe modes. Time to adjust power flows on long lines. Time to reroute polar flights. Quiet engineering decisions save more than dramatic stunts. There is also a lesson in scale. The Sun sends about 1 kilowatt of power to each square meter at Earth's distance on a clear noon, enough to warm skin, run a small heater, or power a modern laptop many times over. Those watts come from fusion deep inside a star and arrive without wires, bills, or switches. The price we pay is variability and risk at the edges. Bright storms that lift plasma into space, subtle changes in the ionosphere that bend radio paths. and rare, large events that test our systems. The answer to those risks is not to throw our troubles at the source. It is to build systems that bend without breaking when the sky changes. The physics that color a sunrise are part of this steady picture. When the sun sits low, light takes a long slant path through the air. Shorter wavelengths, blue and violet, scatter more. Longer wavelengths, red and orange, carry farther to your eye. That is why the last light looks warm, even though the sun's basic spectrum is set by its surface temperature. The same scattering happens above us at noon. Blue is simply what is left after the redder light passes forward. A simple walk at dawn connects you to a chain of causes that runs from a gas in your lungs to the nuclear binding energy of hydrogen in a star. This is a good place to compare simple and easy. Simple does not mean easy. The idea, throw it into the sun, is simple. The steps are not easy. Cancel tens of kilometers per second, survive heat, avoid risk to millions, and pay costs that would squeeze out work we know is needed. The idea, use less, reuse more, store safely, monitor honestly, is also simple. The steps are hard in their own way, but they are within reach, and they spread risk instead of concentrating it. They are also flexible. If a better container or deeper rock proves safer, we can change course. If a lab finds a way to shorten the time some isotopes need to be isolated, say, by transmutation in a reactor, we can adopt it. We do not have to bet everything on one throw. It is worth being clear about trade-offs, because the sun itself is a study in trade-offs. Gravity pulls in, pressure pushes out, magnetic fields store energy, reconnection releases it. Radiation carries heat in the radiative zone. Convection carries it near the surface. The 11-year cycle lifts activity and then lets it fall. We live next to that balance. We read the patterns with instruments and models and shape our choices around what we learn. Disposal to the sun is a choice that ignores the patterns that matter: cost, risk, and control. Think again of the quiet hill at first light. The colors spread because air, simple, nitrogen and oxygen, with traces of other gases, scatters light by wavelength. The warmth on your face arrives because photons finally escaped a crowd inside a star and then crossed a gulf where nothing slowed them. The day begins because Earth keeps its pace around the sun, held by gravity and guided by sideways motion. The dependable return of that light is not a reason to treat the sun as a furnace for our mistakes. It is a reminder that steady answers are better than dramatic ones. We can fly near a star to learn. We can harden our technology to ride out its moods. And we can keep our land, air, and water safer by doing the less glamorous work where our hands reach. If you want a final image to hold, picture a small, dark capsule deep underground, a steel canister of vitrified waste, dry, monitored, and wrapped in stone that moves slower than a fingernail grows. Now picture a bright, heat-shielded probe skimming a few million kilometers above the sun, feeling the young wind and sending back numbers that help us plan. Both are acts of respect for physics, for risk, and for the people who live downstream of our choices. The sun will keep time for us, fusion in the core, light at the surface, auroras at the poles, and dawn on the hill. Our job is to match that steadiness with care.